Another application of the differential is in the computation of errors. Differentials are also used in the approximate computation of certain quantities due to very small errors in cases like when we measure something. So for example, if we are given, say, the function y equals f of x, and there is an error in x dx, okay, this is an error, a very small error in x. It leads to an approximate error. It will lead to a very small error also in y, which is called dy. So this is an approximate error in y. So dy over y is called the relative error, and the approximate, this is the approximate value, and the approximate error in y, that is the percentage error, is equal to the relative error dy over y times 100. So let's solve a problem. The radius of a circle is measured to be 10 centimeters with an error of 0.05 centimeters. We are to find the relative error in the computed area. Okay, so let us look at our values. Our value, we are given 10 centimeters, that is the radius, and we have an error of the radius which is 0.05 centimeters. So r equals 10 centimeters and dr is equal to 0.05 centimeters. So if there is an error in r, in the measurement of r, it will lead to an error in the computation of the area of the circle. Now, we know that the area of the circle is given by the formula pi r squared. So finding the differential of the area with respect to r, so dA is equal to 2 pi r dr. So when the radius is 10 centimeters and the error in the computation of the radius is 0.05 centimeters, so dA is equal to 2 pi times 10 centimeters times 0.05 centimeters. So dA is equal to, that would be pi centimeters squared. Again, this is the approximate error in the computation of the area. So also, aside from dA, or the approximate error in the computation of the area, we also need to solve for the area. So when r is equal to 10 centimeters, this is pi times 10 centimeters, quantity squared, so this is 100 pi cm squared. So this is the area of the circle. So the relative error of the area, of the computed area, relative error is equal to dA over A. So dA is pi cm squared and area is 100 pi cm squared. So the relative error is equal to 1 over 100, or that would be equal to 0.01. Of course, it is unitless. So that is the relative error in the computed area of the radius of the circle rather. Next problem. We are to find the approximate percentage error in the computed volume of a cube whose edge is x centimeters if an error of 2% is made in measuring the edge. So this error is the error made in measuring the edge. So we have a cube. Okay, this cube, the edge of the cube here is x, and there is a 2% error made in measuring the edge, this x here, which means that the given 2% dx over x times 100 is equal to 2. That is the error made in computing or in measuring the edge. Now for the volume, because we are to find the approximate percentage error in the computed volume, so when you say approximate percentage error in the computed volume, percentage error PE is equal to dV over V times 100, right? So for the volume of the cube of edge x, V is equal to x cubed. So that dV is equal to 3x squared dx, right? dV is equal to 3x squared dx. So in the computation of the percentage error, that's dV over V, what is dV equal to? It's 3x squared dx, so we can just substitute this here. So dV is 3x squared dx. And what is volume? Volume is x cubed times 100. Okay? So that this would now be equal to 3. And then we can cancel here x squared over x cubed. So there would be x left in the denominator. Let's just rewrite this. This is now 3 times dx over x times 100. And as you see, this dx over x times 100 is our error in computing the edge, in measuring the edge. So this is now 3 times 2%. So the error, the percentage error in the computed volume is 6%. Alright, next example. An error of 1.2% is made in measuring the side of an equilateral triangle. Find the percentage error in the computed area. So we are talking here about an equilateral triangle. So there is an error in measuring the side, so of course there would be a corresponding error in the computed area. So how does an equilateral triangle look like? Equilateral triangle is an equiangular triangle. All sides and all interior angles are equal. And remember that for a triangle, the summation of all interior angles is 180 degrees. And so because all angles are equal, then each interior angle here is 60 degrees. So if we let x be the side of the equilateral triangle, so this side here is x, this side here is x, and this side here is also x. Okay, so to find the area of a triangle, for a triangle, let's just draw a figure here. For a triangle of an interior angle theta, and here we have here A, side A and B, then the area of the triangle is 1/2 A times B times sine of the included angle theta. That is one of the formulas in finding the area of a triangle. So for our equilateral triangle here, this is one side, this is another side, and this is an included angle 60 degrees. So the area of this triangle, is equal to 1/2 x times sine of 60 degrees. And that would be 1/2 x squared. And sine 60 degrees, what is sine 60 degrees? It's square root of 3 over 2. So therefore, the area is equal to square root of 3 over 4 x squared. So finding the differential, the error in computing for the area is equal to square root of 3 over 2x dx. So for the percentage error, PE, that would be equal to dA over A times 100. Okay, so our dA is equal to square root of 3x over 2 dx, and our area is equal to square root of 3 over 4 x squared times 100. So we can actually cancel out square root of 3. We can cancel out one of the x's, and we can simplify this 4 and 2 here. So what would be left in this case now would be 2 dx over x times 100. So how do we now solve for the percentage error of the computed area? So we go back that they have here an error made in measuring the side of the equilateral triangle. So similar to what we did in the problem earlier, edge is x, so dx over x times 100 is 1.2%. So this dx over x times 100 is 1.2%. So 2 times 1.2, that would be equal to the percentage error in the computed area is 2.4%.